Alright, today we're going to talk about what is called equilibrium, chemical equilibrium and the equilibrium constant. Now I just have the slides on a PDF, so just follow along kind of the same way that we normally do. Alright, this whole idea of what's called equilibrium is going to be the fact that we kind of reach this balance. Alright, so when we talk about the concept of equilibrium over here, it says not all chemical reactions reach completion where the limiting reactant is consumed completely. Okay, in fact, most chemical reactions that occur in living systems never reach completion. Actually, what happens is they produce some amount of product, appear to stop, but they're actually, never fully consuming what's going on. So there's a little bit of kind of moving backwards, so to speak. All right, so if we scroll down here just a little bit, oh yeah, it's going to happen. Okay. First of all, we got to define equilibrium. That's what we're going to do right here. It says chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate in a closed system. Now, it doesn't mean you have equal amounts of products and reactants, but the same rate. Okay, so reactions that attain the condition of chemical equilibrium are said to be reversible, meaning that the products can react to reform the reactants under the same set. And we demonstrate this, if you look down here, with this whole two-sided arrow, or sometimes we also write it like this, meaning that the reaction can go forward, but once we kind of have reached a lot, we can also go backwards as well. Okay, so over here it says as the system approaches equilibrium, both the forward and the reverse reactions are still occurring. So they're still going on, but at equilibrium the forward and reverse reactions are proceeding at the same rate. Okay, so here you have the forward reaction, the concentration of the initial reactants is going down, the concentration of the products is going up, and then once the rates are equal, you have the same amount and they occur at the same rates right here. Okay, that's what it's showing you. Remember, this whole idea of equilibrium is just the fact that the rates are going to happen at the same amount. Okay, so for this whole concept of equilibrium, you have carbon monoxide plus water, and then you have carbon dioxide and hydrogen gas. Remember, equilibrium is achieved once these lines have a horizontal plateau. Okay, so the product concentration will increase, and then once the concentration stays the same, it's at equilibrium, the concentration of the reactants will decrease until it becomes the same at equilibrium. Okay, so here are the reactants that are going down, you were using those up, and the products which are going up. Now for a system at equilibrium from the outside, it appears to be non-changing. It looks like nothing has happened. But reality, it's going in both ways. It really can only exist on a closed system, and it's all based on ratios. Okay, ratios of reactants to products, and that's the whole premise of equilibrium and what it looks like. So if we flip the page here for me. Now again, equilibrium can be reached from either direction. And this ratio is going to always stay the same at a constant temperature. Doesn't matter what you start the reactants with, it's always going to level out. Now what happens is we get this stoichiometric connection and what's called the law of mass action, which is pretty much an idea that the coefficients of a balanced chemical reaction can help us describe that ratio. Okay? So, just bear with me, we're almost there. About as simple as I can get equilibrium right here. So from the law of mass action, if this is a general reaction where the lowercase letters refer to the coefficients, the uppercase letters are the chemicals themselves. This is a little bit tough to see, so I want you to write this. But you'll notice these refer to the products, these refer to the reactants. So you have the chemical itself raised to whatever power or stoichiometric coefficient. Chemical itself raised to the power or the stoichiometric coefficient. Those are the products. And then on the bottom you've got the reactants. So there's the chemical and its coefficient, the chemical raised to the coefficient, a little off there. Okay, K is what we refer to, is equal to K, as the equilibrium constant. And pretty much what you guys have to be able to do is write these constants and solve for K. And that's it. So for a system at equilibrium, the equilibrium constant Kc describes not only an equal and constant rate for the forward reaction, but also a ratio of where they stay the same. The concentrations or the pressures don't change. Now, so what do we have to do? Well, again, there's two types of problems, and this is the last two things that we're going to do right here. Number one, we have to be able to write equilibrium expressions from reactions. Number two, we need to calculate the equilibrium constant for certain reactions that were already given. So let's focus on this first one right here. All right, and I'm actually going to cross off letter B for a reason. So for right now, don't worry about letter B. We're going to focus on A and C here. And remember, we just have to do a ratio of products to reactants, and that's it. So if I bring up a notebook here, we'll try to slide this over so we can see them both on the same screen. If I'm looking at this one right here, my equilibrium expression, my K, is equal to, remember, the products go on top. So I'm going to have nitrogen dioxide raised to the second power simply because it has a coefficient over my dinitrogen tetroxide, which does not have an exponent here because it's only to the first power. I could put the 1 there if you want to always put a number. That's it. Okay, and that's it. That's the whole thing. That's the equilibrium expression right there. Entire answer. Okay, now for letter C, let's do the same thing. And remember, this is our equilibrium expression, and we're going to have hydriodic acid, that's my product, raised to the second power because it has a coefficient there. And then on the bottom we have the concentration of hydrogen gas as well as the concentration of iodine gas. And this is it. This is the equilibrium expression for this particular reaction. Okay? Now the other thing that we got to do, so that's it, equilibrium expression, balanced chemical reaction, raise it to the power, put the products on top, the reactants on the bottom. Alright, next thing that we got to do, I'm going to come over here, is calculate the equilibrium constant for the production of hydrogen monoiodide, as we call hydriodic acid, if the following concentrations were determined at equilibrium. Okay, so let me jot these down first, and then I'll just bring up the Power Smartboard app here. So my hydriodic acid concentration is 3.1 times 10 to the negative second. They have moles over liters, which is the same as molarity. Our iodide concentration is going to be 8.5 times 10 to the negative first molar. And our hydrogen gas is going to be 3.1 times 10 to the negative third molar. Okay, so to find the equilibrium constant, literally all I have to do is take these numbers, right, and plug them into my equilibrium expression, because what we're solving for, what the unknown is this K value right here. Alright, so let's plug and chug and see if we can get a correct answer. When do I want to do this? Let's do it right here. Okay, so I'm going to have 3.1 times 10 to the 10th times 10 to the negative second, and I got to square it, over 3.1 times 10 to the negative third times 8.51 times 10 to the negative first. Okay, all I did was take these numbers and plug them in. My hydrogen goes in for my hydrogen, my iodide goes in for my iodide, my hydriodic acid goes in there. And I solve for it. Now this is just mathematics, but if I reduce it, the top part is going to be 0.00961. The bottom part is going to be 0.002635. That's just doing this math. So I get a final answer of, and all of my data points had 2 sig figs. My calculator is going to give me 0.3647, so I'm going to do 0.36, and there is no unit on this one. Okay, capital K is simply 0.36 with no unit.